On 4.3 problems, I'm going to start with number 3 because I think the other stuff probably isn't worth that much time, but this one does present some interesting points. So this is already arranged in order, but I'm going to explain why it's this order. Now, you would need to do some research and find some KB and KA values, which they don't exactly say. But if we pretend that we did that, we can get some data and then we can arrange this. We know that KNA, KNA, and O3, Cl are all parts of strong acids and bases, so they're not going to contribute to the changing of the pH in water. So let's consider the other things. So that's why we have a Kb of Cn minus. It is possible that could draw in some H plus and act as a base. The same goes for the acetate ion. Neither of these, so that's going to be neutral, and the pH would remain at 7. Now, about this ion, I know some kids will say, but it's negative, and you just pointed out that negative things attract H. But consider what negative ion we're talking about once the sodium leaves. This is the conjugate base of a strong acid of H2SO4, so this has just zero chance of drawing an H back onto it, which is why we didn't go looking for a Kb, because the Kb is just like nothing. However, it could donate the second H, and it could, and it really might. That's not a bad number at all for what we consider a weak acid. That's sort of a strong weak acid. It's one of the stronger weak acids, if we can say that. But it would create an acidic situation. So when we look at all these, I'm going to ignore the zinc one for a minute. We get a Kb of this, a Kb of that. So let's compare these two. This is a stronger Kb, so this creates a higher pH than that one. They both create pHs higher than 7, because that's what pH for basic situation is. So they rank in this order above something that keeps the pH at 7 when you add it to neutral water. This creates an acidic situation, so we know the pH is below 7. And the weird comparison is the zinc. And I really had to do some thinking and a little bit of internet sleuthing for this. And we cross out the nitrate because it doesn't matter. And I know it says it's acidic, and a kid will be shouting in the brain, you said acids give off H plus, and it doesn't have any H. That's true. However, this cation could be attracting OH minus, which would remove OH minus from the water situation where it was there naturally from the dissociation of water that happens naturally. And that would change the proportion of H plus to OH minus, which would make it heavy on the H plus because you just tied up OH minus, and that would make an acidic situation, which is why I put it creates an acid solution, not it is acidic, if I can split that hair there. Could zinc attract OHs to itself? Sure. And what I found was a KSP for this. So let's pretend for a moment that we knew we had zinc hydroxide, and if it dissociates, it creates one zinc ion and two OH minus ions. And the KSP for that is very small. It's 3E negative 17. So if we run that backwards, which is what we're talking about, right? We're talking about the zinc taking OH onto itself, then we're running this backward. And therefore, if we flip it end to end, if we reverse it, the K is the inverse of the previous K, which means it's very large. This does a great job of tying up hydroxide. If you can manage zinc cation in water, it will tie up hydroxide ion very well. And I bet it's doing it much better than even this is dumping in H plus, because it looks like it ties up a lot of OH minus, a lot, which makes a pretty darn acidic a situation. So this is being a better base than that one. Both of them are being a better base than something that is neither. This is being an acid, but only a moderately good one, not a strong one. And this apparently is doing a great job of tying up OH minus, and I'll bet it pushes the pH down even below whatever this one achieves. And that's why they're in this order. On number 4, they ask us for the acid dissociation reaction for the bicarbonate ion. So we write that out, and of course that's the K expression, and we just look up the K value. So if that's the K value for the Ka, then what's the Kb? Well, it's 1e negative 14 over the Ka, of course, which generates this. And so does this create a basic or an acid solution? Well, which is it? Is it a stronger base or a stronger acid? And this is decidedly bigger than that, so it's a stronger base. So if you put in a sodium bicarbonate, you get a basic solution. 5 is kind of such a layup that I almost skipped it, except that they really think you know this. It just boom, boom, boom on a multiple choice or something. If that's the Ka, then what's the Kb of the ion here? Well, it's 1e negative 14 over that, right? So if they said that they put in KOCN into water and they gave you Ka of HOCN, they expect you to say, well, K isn't going to matter. What I've really done is contributed OCN minus to water. They gave me KN of this, which I don't have. And this is the mental leap you very much are expected to make. But they gave me Ka of the acid, and I have the conjugate base. And this is the math that will get me Kb for the reaction I will really get, because what I will really get is that creating the acid, huh? For number 6, we just need the Kb of the conjugate base of phenol. If that's the Ka, okay, then what's the conjugate base? I don't even have to know. I just have to know that the conjugate base's Kb will be 1e negative 14 over the Ka. They told me 7.7 e negative 5, and so it slots in there. On 7, we have the question of whether this equilibrium would favor the products or the reactants. And the question comes down to kind of which one is a better acid, the ammonium or the water. Because if we go forward, water is the acid. It donated an H plus, there it is, and it's missing the H plus. Notice if we run backward, the NH4 has donated an H plus, and now it goes back onto the hydroxide. And this is now back to being water, and the NH4 has turned into NH3. So, which is a better acid? Well, the Ka of water is 1e negative 14. And I know somebody's kind of shouting in their head, that's Kw. Well, it's both, because you get one H plus and one hydroxide in pure water. And we know the value of each of those is 1e negative 7. And Ka then would be those two multiplied and not divided by anything about water, because that's a liquid, so that doesn't figure into K math. And so it would be the H plus molarity times the OH minus molarity, which is also Ka. Another way of naming that would be Ka. So the Ka of water is 1e negative 14. If we look this up, we have a Ka. So in the fight about which way this is going to settle, we pick the one that's using the better acid, and this Ka is definitely bigger than that one. So this equilibrium will be an equilibrium, but it will tend to settle with more reactants than products. These two are pretty much the same thing. I'm going to skip ahead. On 8, we have a 0.8 molar solution of a weak acid. Don't think that that's SO4. This is not a strong acid. So we have a Ka1 and a Ka2. I know they didn't write A, I wrote it in. So this is the value for taking off the first H, and this is for the second. Notice the second one is always weaker. It's always a weaker acid. It wants that second H more than it wants the first one. It holds on tighter to the second one. What's the reaction? This will create 1H and HSO3 minus. See here. So here's the products, and this, of course, is the reactant. And destroying one of these will make one of those and one of those. So we get X and 0.8 minus X. Now with a Ka this big, you cannot really cross out minus X. So use the quadratic formula. I'm going to say, let's pretend we did. There's the value of X. X is the value of H plus and the HSO3 minus, which means we can take negative log of this value and get pH. So the original amount turns into 0.8 minus X, and we get this for the new value of the H2SO3. If we continue on and take off the next H, remember we're not dealing with this anymore. We've used up all the H's it can manage to donate. We're going to deal with this as our new continuing on acid, and this value is that value. So one of these will get destroyed and create one of these and one of those. So remember also H plus was starting now with this amount created by the first H coming off. So one of these gets destroyed and creates one of these and one of those. So this will be the starting amount plus X. This will be simply X, and this will be 0.1 minus X because it's losing amounts. However, this Ka is so small that adding and subtracting X won't matter. I'm going to cross them out. solve for X, and that X is the SO3 2 minus molarity. Also, though, um, we can notice, which was put in another problem earlier, that the pH doesn't effectively change, because what does the H plus value do? Well, essentially nothing, because we just said adding this much H plus from the dissociation of this will be too small to notice. This Ka is too small to put in enough H plus that when we add it to 0.1, anyone cares. No one cares. So this H plus value is going to stay essentially the same for all practical purposes, and the pH won't move. So actually doing this math to find the change in pH turns out to be pointless, which actually we could have known if we have some experience just by looking at this Ka value. You could say that is not going to put enough new H plus into the solution that I'm going to care, and I'm not going to bother doing all this and finding the new H plus molarity so I can get a new pH. I'm just going to say that the pH remains unchanged from 1, which in all practical purposes is true. On the old AP question, they start off pretty easy because they just ask you which is the stronger acid, but they told you the Kas, so the bigger Ka is the better acid by definition. They do think you can do some pretty easy, I admit, Lewis dot diagrams. So they really might ask some, but they don't get overly complicated and they don't get into resonance structures and stuff like that. But they will ask you to do something that's like this, or maybe slightly more complicated, like they might ask something like CL OH or something, but nothing that complicated. So make sure you know how to do this. The halogens, the halogens are the F family. They all have 7 valence, so they tend to want 1 covalent bond. Oxygen has 6 valence. It tends to want 2 covalent bonds, and obviously hydrogen can only have 1. They don't test you on the naming like this. They gave you the formula in case that is gibberish. They tell you the formula, but they do expect you to answer the question with a good reason. So, and you have a periodic table. So remember, it goes F, Cl, Br, I. So I is the farthest down the table, which means it's the least electronegative. And they expect you to know that up toward fluorine is the most electronegative part of the table. Fluorine is the most electronegative, meaning that it holds electrons to itself the best, or more accurately, it seeks electrons from other things the best, but it's pretty much the same thing, which means that iodine is the least electronegative out of itself at Cl and Br. And notice they didn't change the formula, so it's still going to be an O in the middle there. So I is less electronegative, so that the bond to the O is pulled away less, which means that the O is going to pull away this bond less, which makes this H less pickable by another chemical, which means it's a worse acid. So it's a weaker acid because that bond is stronger. A weaker bond here would make the H more grabbable, and that would be a stronger acid. And then this is just free points. We got to be able to do that with our eyes closed, that some acid contributes H to water, and they do mean to write the hydronium here. They did say and water here, so it's tempting maybe to put an H plus out here, but they said and water, so we got to use water as a reactant and generate hydronium. On C, we are expected to know that the NAs, of course, will come off, which means really we've donated OCl minus to water, and that is going to be a base because it's attracting H plus, and that is very much not a strong acid that you would be forming. So could it attract H plus? Yeah. And would it stick? Oh, yeah. Now at the top, they told us Ka of HOCl. So when we're going to run this backward, notice that this is the acid reaction backward. Then the Kb is Kw over the Ka they provided at the top. This has got to be almost in your sleep by the end of the course. Products over reactants to the power of the number in front. Don't put water. Oh my gosh, don't put water. And so what is OH minus? And again, we got to start doing these ice boxes in our heads, I think, just for time's sake. This is going to be 1.2 minus x, whatever that x turns out to be, plus x plus x. So we're going to get x times x on the top, and 1.2 minus x, and double check my KB is this, write that in, and it is definitely 3 decimal points or smaller than this. It's a lot smaller, so we can cross out minus x and solve for x. What is x? What were we looking for? Which I admit I forgot to sort of note to myself. We are looking for the OH minus concentration. I solved for x. That is the OH minus concentration. Remember, we started at 0 hydroxide and ended up with x at the end. So x value is hydroxide ion concentration. Don't forget the unit. So on D, remember that a buffer is made by a weak acid and the conjugate base, or a weak base and the conjugate acid. If you don't remember what I'm talking about, hit pause and replay that. Go look it up, but this is probably going to come up at some point on the test. So if we dissolved this in water, again, the NAs come off, and really what we've added is the OCl minus, and that is a weak base. It's not a strong base, but it is a base because it could take H onto itself, which we just proved back here. In fact, we have a KB for it, don't we? And we put in the conjugate acid. So we stick in a pH probe, apparently. We find out the pH is this. So back to intro class, actually. This is literally my class, an intro class question. What's the H3O plus molarity if that's the pH? And it's 10 to the negative pH, or its inverse log of negative pH. That's literally the same thing. And we find out that this is the answer. Don't forget to put molarity H plus or brackets. Now, the difficult part of this whole side of this page, at least, is definitely DII. Which is there more of, this or that? And it might seem like that's just impossible. Well, when you hit with that situation, what equations do you know that deal with pH that maybe you're not thinking of? And which one deals with the proportion of base and the conjugate acid? And the answer is the Henderson-Hasselbalch equation here. So if you need to, you flip to go find it. It's probably best if you memorize it. I remember that the minus goes on the top. This is often written as log of A minus over HA. That's probably the way it's written in the booklet. So the bigger piece is on the bottom as the foundation. Maybe that's a mnemonic, so you can remember which is on top. The base is on the top. So this is on the top. The conjugate acid is on the bottom. So they told us the pH. We can put that in. We figured out the K. No, they told us the Ka back at the top. There we go. And it's plus the log of the proportion, isn't it? So we can take the negative log of this. We get that. And then we can subtract it back over here, and we get this. Now, the log of the fraction is equal to this. So I went and wrote some things in. There's a few ways to look at this. You can either just simply hit inverse log of that and find out that the fraction is 0.089, which means that the denominator is larger, isn't it? For something under 1, the denominator is larger, therefore the acid is more prevalent. So the concentration of the acid is greater than the concentration of the conjugate base, isn't it? And state it really clearly. And don't forget to put brackets or molarity and say larger, greater than symbol, and so forth, and have some very good math logic where they can't deny your point. Don't just write a conclusion in any sense. Also, I want to point out this. We have sort of 3 brackets for the possibility of logs. The reason there's not a 4th one is because you can't take the log of a negative number. So we can't break the 0 barrier here. So we have 3 possible categories. The dividing line is 1. You can take log of 1, and the answer is 0 because log of 1 means 10 to the what power will get you 1. What's in the box? What's the exponent? Box is 0. 10 to the 0 power will get you 1. Well, you can do it also for something less than 1. So I just put 0.5 just as an example, and I did it on the calculator because I couldn't do that in my head. And so 10 to the what power will get you 0.5? And the answer is negative zero point 0.3. And you can try it on your calculator. I would make sure that you can really sling these log functions before the end of the course. So go do it now. And just as an example of greater than 1, log of 10 is 1 because it means 10 to the what power will get you 10. And of course, 10 to the first power will get you 10. So log of 1 is 0. Log of something greater than 1 is greater than 0. And log of something less than 1 is less than 0. You can have the answer be negative. You can't take the log of a negative number. Don't confuse those two. There is no power you can raise 10 to generate a negative number. So if you want, go to your calculator and put in log negative 10 and you get error. You can't take the log of a negative number, but the exponent can be negative on 10. That's what this is. I'll point out that this is from 1990 and they don't really ask these long-winded explanation questions anymore, but it's good practice. So first of all, I'll point out that dissociation constant is usually their phrase for K, and we've got to know that right off. A diprotic just means it has 2 protons, 2 H's, not really important exactly. You could skip that if you had to. So for hydrosulfuric acid, the first K, so K1, is larger than the second by about 10 to the 5th, and then they tell you, look, this is much larger than that. So does that mean it's a better acid or a worse acid? K1 is much, much greater than K2, right? You have to multiply K2 by 10,000 to reach K1. So it's tempting sometimes to get this backward and say, oh, this is bigger. No, it's not. You have to multiply this value by 10,000 to reach that one. This one's much bigger. Plus, they said the first one's bigger. So why is that? Well, this acid has 2 H's to give, but that first one is much more grabbable than the second one. So whichever one encounters a good base first goes, but whatever the first one was, that one's much more pickable, and this thing is much more reluctant to give up the second one. So the K value for this second one is much smaller. Explain how this is a base and this is an acid. That's funny. This is an acid because it can give H plus, and I know that this does not give H plus itself, or excuse me, and why is this a base and that's an acid? That's kind of funny. Obviously, this is an acid because it can give away H plus. This is not a base because it takes H plus in this current form, but obviously all the sodium's going to come off, and that OH is a spectacular H hunter, and it is going to grab up any free H plus it can find. And so, yes, you get that is a base. When this comes apart, that is very much a base, and it will make water, of course. And so you need to mention that when the something along the lines of the OH minus is going to come off because the sodium salts are very soluble, at which point the OH minus will be grabbing H pluses and being a base. And this one will be donating H even to water, sometimes making H3O plus. So this one, I didn't even honestly recall, but I do see their point. We said both of these are strong acids, so they come apart at essentially 100% in water, and I wouldn't have made any distinction between them. And their point is that's true in water because water is such a good acceptor that you can't tell the difference. If you give them, though, a difficult situation, it turns out that HI is a better acid. HI is a stronger acid. And why? Because we said before, the bigger cloud away from the nucleus means that the H is more grabbable, which makes it a better acid. So when you give it a difficult situation, you're going to start to tell the difference. I mean, if you grab some random NBA player and put him in a free throw contest against Stephen Curry, it might be hard to tell the difference. What you need to do is have a 3-point contest, make it difficult, and then you can see the differences in the talent here or in the acidic quality. That's basically the same reason here that the CL radius is bigger than the F radius, which means that H is not so well held. It's weaker. The bond is weaker, which makes the H more grabbable. It's more acidic. It's more able to be grabbed away, which makes it a better acid.